Sir, Manik Vasagam, sir. Can we start the session, sir? Can you hear me, sir? Am I audible, sir?
Check.
Yes, sir. Can we start the session, sir?
Hello, Manika Vasagam sir, can we start the session?
Yes, ma'am.
Okay, sir.
A very good morning to one and all present here. On behalf of the Department of Biomedical Engineering, in association with NextGen Biomedical Committee, NBC, I extend a warm welcome to everyone gathered for today's faculty development program on recent trends in biomedical engineering. And heartfelt thanks to our Honorable President, ACS Arun Kumar Sir, for this opportunity. I am Rubina Jurid from third year BME, Joint Secretary of NBC, and I will be a comparer for today's program, guiding you through the flow of events. We are indeed privileged to have with us a distinguished faculty members and our respected speaker, Dr. R. Manikavasagam. Now, it's time to introduce the driving force of today's knowledge session, our esteemed speaker, Dr. R. Manikavasagam. For the formal introduction, I invite Ms. Nitya, third year BME, additional manager of NBC, to introduce our speaker for the day. Over to you, Nitya.
A very good morning to one and all present here. On behalf of Department of Biomedical Engineering, it gives me an immense pleasure to welcome you all to today's session, a 5-day virtual faculty development program on recent trends in biomedical engineering, organized in association with Academic Staff College and Extend Biomedical Committee, NBC. We are truly honored to have with us Dr. R. Manika Vasagam, Vice Principal and Head, Department of IT and Artificial Intelligence and Data Science, Alpha College of Engineering, Chennai. Sir is also serving as the Joint Secretary of Biomedical Engineering Society of India, BMESI, for the period of 2025 to 2027. Dr. Monica Vasagam holds a PhD in lung nodule detection and classification in CT imaging using computer-aided diagnostic technique from Anna University and has over 22 years of teaching research experience. His area of expertise include medical imaging processing, deep learning, pattern recognition, soft computing, and computer networks. He has published more than 30 research papers in reputed journals and international conferences and has successfully completed 2 sponsored projects. Sir has also delivered numerous expert lectures and organized many FDP seminars, workshops across the country. We are indeed privileged to have such a distinguished personality with us today, and we look forward to gaining a valuable insights from his vast experience and knowledge. Once again, we extend a warm and respectful welcome to you, Dr. R. Manika Vasagam, and to all the participants joining us today. Thank you.
Thank you, Ms. Nitya, for the wonderful introduction. We are truly honored to have a speaker with us today. Sir, over to you, sir.
Thank you. So, good morning, all of you. Thank you for the organizing team. Actually, I thank the management of Dr. MGR Educational Research Institute, and the leadership team for giving me this wonderful opportunity. And particularly, I thank HOD Dr. K.S. Divya Madam, and even coordinators Dr. F. Variza, Deputy HOD, and Mrs. B.R. Sankari, Assistant Professor. Particularly, I'd like to thank Ms. Saranya, who invited me actually for this FDP. And thank you for the MC team for your nice introduction and the beginning of this session. And I'd like to thank and wish to all the participants because you have spent time to learn new things before commencement of the next academic semester. So I thank all the participants for your time you spent here for the new learning. Let me share my screen and I'll start present. Hope my screen is visible to all of you.
Yes, sir, it is visible.
Yes, thank you. Okay, we are sitting here for the FDP on recent trends in biomedical engineering, which is organized by Department of Biomedical Engineering from Dr. MGR Educational and Research Institute. Actually, my session schedule was yesterday 2 to 4 p.m. Due to some academic related engagement, I could not able to make it. So I requested the organizers, and organizers have changed the schedule. So maybe for the participants in a day, 2 sessions, it is difficult for you maybe. How much it is possible for me to comprise it within the stipulated time, I can do that. And my topic for the FDP session is innovations in computer-aided diagnosis for clinical decision support. I'll move on. This is my presentation overview. So computer-aided diagnosis, we want to understand about what is computer-aided diagnosis. Maybe many of you may come across. Maybe I formally introduce, then I can move forward. And what is the motivation towards this innovation is essential towards. And next is CDSS. Next, I'll talk about early methods which are developed in various departments of medical domain. And there is a need for integration of systems. I'm going to talk about the same. And particularly, I have worked in the area of the computer-aided diagnosis for the disease diagnosis. I have worked in the domain called lung nodule detection. So maybe I'll come up with maybe when I talk completely theoretical, maybe the participants will not feel good about it. So I'll say about the implementation and each and every part of the development of this method. 2 methods I'm going to talk about: SVM based classification and ANFIS based classification. So these are all machine learning methods, and it may come up from the traditional methods. And later on, right, I'll talk about limitations of this conventional method, and maybe I'll give some inputs related to the deep learning approaches which are used. Maybe I have used post PhD. I am keen on working with deep learning approaches. So far, I have completed 2 projects in deep learning approaches. I don't know whether the time permits to discuss all that. If not, maybe some other occasion we will discuss about. Then let me summarize all that, and I'll complete my session. So first I move on to the computer-aided diagnosis. So this is a formal definition for the computer-aided diagnosis. is a medical technology that uses the software and AI techniques to assist the healthcare professionals in interpreting the medical images and other diagnostic data. So we want to diagnose the disease and particular about what is the depth of it, what is the stages, what is the type, and what is the growth. All that we can able to determine by using this method. So the very motivation of this particular topic which I have given for the DP session is that CAD is always used as a second opinion for any patient for that matter, or medical professionals as well, and which significantly improves the diagnostic accuracy. So this is one key area, right? We need to think about the promising method as a computer diagnosis for the disease detection or early detection of the disease and so. So maybe I'll introduce what is a general CAD system all about in medical domain. So normally, right, the image will be taken from the scanner and which will be passed on to the techniques for the pre-processing techniques. And later on, right, it is about segmentation, what is the region of interest, work in that area for the diagnosis of the disease. And as it is a machine learning and software-based technique, the feature extraction and selection is very much required. And the feature selection is some algorithm which will be selected. Feature selection is some algorithms is selected, and some algorithms may not be required feature selection. Maybe I'll talk about feature selection, which I used in one of my technique that I'll narrate about. And based on that, the prediction will be done. The classification will be done. The classification initially, right, it will be a 2-class classification, which means a binary classification. So nowadays, right, most of the cases it is not a binary, multi-class classification. So maybe the second technique which I have worked on and I would like to present, it is a multi-model, means multi-class classification. I'll give you the details about it. So I'll move on with the presentation, start from the evolution of this system, the CAD system. It basically starts with the rule-based system and later on moved, and nowadays, right, it is happening with the AI-driven system. So the rule-based, we know very well about the explicit if-then rule and logic functionalities for the same. And AI-driven, it starts from the machine learning approach. The earlier 1950s, the specific task for the more dynamic and adaptable systems were developed. But later on, right, it is moved to the recognition of complex patterns and the critical perspective of the disease. So far I talk about CAD. Now new thing, it is about CDSS, Clinical Decision Support System. So what is clinical support system is all about? The same tool can be, the similar tool can be used to diagnose the system, where the CDSS will not stop after detect the disease. It will move on for the therapeutical suggestions. So it basically, right, work with two domains. One is computer-based and non-computer-based. And computer-based, there are a lot of interventions based on the tool for the prediction. It will be captured and it will be processed further. When we think about non-computerized tools, it's core clinical guidelines. The resources like clinical key, up to date, there are several methods. The clinical support resources are available. So based on that, it will be work on. Excuse me. Any clarification is required? Maybe somebody switch on the mic. like to clarify anything? Can I go ahead? Because I'm in the presentation mode, so.
Yes, sir, you can go ahead, sir.
Okay. Okay. So I talked about two terminologies, CAD and CDSS. Now I would like to relate these two. Maybe it may be useful for the further understanding and further discussion. So CAD already I had told you, right? It is for the diagnosis, deduction. Sometimes it is for the classification. Whereas CDSS, it will not stop there after deduction. It will go for it will give the suggestions for the treatment and medications, and it primarily look at the all around patient safety. So this is what the CDSS. Now we are keep on following the CDSS. CDSS maybe the CAD is a subclass of CDSS. Maybe you can take in that perspective. And the clinical key clinical areas. So mainly these are the clinical key areas, but not limited with. Basically, we use the image as the source for our CAD system. So either from radiological or pathology or cardiological nature, and based on this image we are acquiring from the scanner, it can be given as an input to our CAD system. When we use CAD system, maybe I'm not going to talk about CDSS here because my primary objective for the discussion is about CAD system. Already I had compared with, maybe relate with CDSS with the CDSS with the CAD. So challenges what we face in CAD system is that the diagnosing accuracy and the efficiency of the overall system. So these two are quite challenging for us. What tool we can select, how we can take the input, how we can process it, and how we do arrive a solution, which means identification of the class, and that matters about these two terminologies, accuracy and efficiency of the CAD system. So, and I think these three terminologies you may be familiar with: data and imaging. So these two basically we are giving to the CAD system for it to take the decision whether it is true positive or it is false negative. Maybe these terminologies I'll come up with my method. So I literally talk about the traditional statistical approaches. The regression analysis and hypothesis testing, and the statistical measure of the given data, given image or features that will be used for the prediction. But basically the traditional statistical methods use a small number of variables. Basically these methods are primarily used for the purpose of two-class classification or binary classification, even multi-class, maybe 3-class or 4-class, not more than that. Now with the deep learning, right, 1,000 class, 22,000 classes, all that is happening now. And feature-based learning. So already I have mentioned with the CAD system, we need to extract the features from the image, and based on the features, we do predict. And some of the methods such as SVM, random forest, decision tree, this can be used for the different applications to get the pattern and the classification. So from the diagram, maybe this slide can be understand about. The segmentation is the one we have to select the region where we need to look at and look at further for the diagnosis. And from the ROI, region of interest, maybe we'll get the features like edges, texture, colors, maybe statistical feature also we can use for that matter. And with all this, right, the prediction can be done so. So rule-based system, if then rules, maybe I'll explain in my working model. So early neural network, it was used BPNN, backpropagation neural network, which uses the feature-based recognition and for the classification. So CAD and radiology, maybe a lot of images, X-ray, CT, mammograph, MRI, fMRI, right? SPECT, all that is nowadays is more popular and to have. Is basically used to find the microcalcification from the image to detect the nodules and it locate the suspicious lesions. And pathology now the artificial intelligence and machine learning which is used to WSI, it's about whole slide images which has the purpose automatic tasking and quantifying the features and improve the diagnosis accuracy and efficiency. So this is basically a quantitative method for the diagnosis in the pathology domain. And the integration of the system is very well required for now in the current scenario. So PACS is integrated with HIS, which is already associated with the radiological information system, and which is very crucial for the decision making with the following perspective. One is streamlining the workflow. The process has to be aligned with the specific way for the patient to patient and for the system to system, and improve the data consistency. Once we predict the data from the image or the system, it has to be consistent enough to go further for throughout the treatment, throughout the process of the diagnosis and treatment. And these two can be done only for the very purpose of the patient care, the promising patient care. Hope I have finished my first module of my discussion. It may be very generic and maybe I'll talked about a very theoretical manner. Hope the session was informative. If you need any clarification or any questions, maybe you can post. I'm moving on to the second phase. Anybody would like to clarify anything or any questions you have in mind to, because the same discussion I'm going to go ahead with the implemented methods. Okay, I didn't get any responses, so maybe I assume that there is no clarification or no is required as of now. Okay, let me move further. Okay, the first method which I'd like to present, the implemented method, SVM-based lung nodule detection and classification of stages. So there are 4 stages and 5 classes we are taken. And for the segmentation, I had developed the method called GSEM, gradient active counter method. Active counter method is quite popular, and I developed the method called gradient active counter method. And for the resolution, multi-resolution for the texture pattern, I used DWT, discrete wavelet transform. And GLCM features means GLCM I have used for the feature extraction, gray level co-occurrence matrix. And CBH is a method I had developed for the feature selection, consistency based hierarchical method. And SVM is a classifier I use for the stage classification of the lung cancer. Already I have mentioned about 5 classes I have. This is a proposed method, the implemented method. initially pre-processing, next GSEM, and the GSEM is used for segmentation, and this is for the multi-resolution, maybe enhance the feature set, and this is for the feature extraction GLCM, and CBH PCA based classification I have done over here with consistency and correlation measures, and classification by using SVM. This is active counter method. Maybe many of you may aware, right, what is active counter method. So it basically predict the boundaries, and the exact boundary will be extracted with a curve evolution method, and based on the curve and the boundary, the object will be, foreground and background details will be isolated, and the edge, the energy associated with it will be counted for the edges. Now I present about the method called GSEM, which I have used, I have proposed and I have implemented. GSEM. So this is actually basic curve method, means basic active counter method, and I have used the contour modeling with the gradient position, the gradient values. Maybe I'll present the details over my outputs. So based on this, the gradient value, the fixing of gradient value, the ROI will be selected. So here are the details. What are the parameters I have set for my method? So initially I pre-processed, then the gradient value I kept as 0.5 based on the experimentation. I have did several experiments and I kept it. And I have used the iterative curve evolution method for the level set function. And the signum function which I have used with the value 1 for the different interfaces, so for the object boundary deduction. So this is basically the sine function which grow the curve, which grow the boundary, and C is the parameter is evolved with the boundary, means curve. And with that note, I have started with the equilibrium or null condition, initial condition. And initial condition, this will be obtained. And with the mean curvature value for the motion reduction or improving the curve based on the iterative method. So the mean curvature which I used for passing through the axis, and particularly I used here, I set the value of iterative count as 1,000 for the curve evolution. This also I tried with the experiment. So when I use less than 1,000, maybe I have observed discontinuity in the edges. When discontinuities in the edges are there, then the proper curve will not be evolved, which may lead to misdiagnosis of the disease deduction. Maybe I spend quite a long time to develop these models. I don't know how the participants can understand about this. Maybe in particular about any support or anything, maybe I'll give you my contact details later on. Maybe we can work on with, and you can get the clarification later on, but I cannot able to say it is a method developed and which was published also. Maybe you can refer to my publication to know about all this. Okay. And this the active contour methods steps. Initially the contour is evolved with a mean curvature, and here the value tau initially we kept as a constant and it's supposed to be greater than 0. And G of del I is a stopping parameter. Where do I stop my curve evolution? Though I set iteration count as 1,000, sometimes the curve evolved before some images, the curve evolved completely before 1,000 iteration also. This is the function stopping function, edge stopping function. with a Gaussian parameter. And throughout the complete research, right, I have used 2D images. I have not touched upon 3D. Maybe I am working on 3D images now with the deep learning. And these are the parameters which I have used for the purpose of geometric variation coefficients for the pixel and input images, mean curvature on contour, and size is shrinking or expanding factor, because curve is going to be expanded, curve is going to be shrink, maybe reduce or expand. So I kept the value for the tau 0.7. Why I kept 0.7? Maybe I'll come with the later pointer. Next thing, DWT. DWT is most common, right? Everybody may be aware of this multi-resolution perspective, which I'd like to have for the feature set enhancement. 4 subbands I can able to, 2 level I have used. So 4 subbands I can able to achieve it. LL, LH, HL and HH. The Obesius filter I have used for the same. So this is the details about 2D DWT with the parameters. Here I have used H is horizontal, V is vertical, and D is actually the direction of thing. What direction we have used, 90 degree or 45 degree and things so. And particularly the features which I have extracted for the classification, about 18 features I have extracted. Already I have mentioned with my initial step, like GLCM features I have used. Gray level co-occurrence matrix features. These are the 18 features, contrast, correlation, and its relationship is given. I'm not here to explain in detail about these things, maybe it will prolong the discussion. Autocorrelation, inverse difference movement, energy, entropy, inverse difference, prominence, shade, dissimilarity, sum average, maximum probability, difference entropy, variance, difference variance, sum entropy, sum variance, and lastly about information measure of correlation. These formulation were given by the Haralick, and based on the Haralick method I have extracted the features from the given image. So in my consideration, there are totally 18 features I extracted from each subband. So already with the DWT I have 4 subbands, so 4 into 18, right, 72 features I have in hand for the prediction. And maybe the 72 features are too high for the processing, and some of the features are not prominent and which are very much useful for the prediction. So in this note, I immediately look at the feature selection process. So this is the need for the feature selection. Since more features, time will be high and some are not prominent, and it is time consuming training process also. And in this case, right, I supposed to identify the suitable subband for the classification, for which, right, I have developed the method called CBH method for the feature selection. This is a method I have used, and GLCM feature extracted recently I explained. Excuse me, yeah. And these are the 4 subband images are coming to this, so totally 72 features. And here 2 level feature selection with the help of PCA I have done. One is consistency measure, another is correlative measure. I'll explain about consistency and correlative measures, what I took place, what I took developed. PCA and the feature selected. So first I'll go with the consistency measure of the subband selection. So maybe 4 subbands of DWT I have used distance measure for each subband and each feature which are available. So I calculated the distance of extracted features and assess the features consistency. How consistent the features are rely on with the decision making. So the feature with the distance above 0.7 is being selected and considered as a consistency, because the Cronbach's rule I have used for this particular thing. 0.7 is more consistent, and when we select less than 0.7, that are not that much consistent towards the decision making. That's the consistency measure. Next, I move on for the correlation measure. Correlation measure, I do evaluate the correlation coefficient R based on this expression. And here A and B are the features. Maybe two features I take and correlate with them, and which is more correlated, and with that I'll take. Parameter N, which I have used here, is a number of input. So as of now, the number of input will be based on the number of images I have. The procedure will be repeated for all all four subbands and obtain the correlation values. Maybe I listed down and I'll show you. Here I have used Pearson product moment correlation to select the features with a correlation coefficient value above 0.5. Okay. So as per the Pearson product moment correlation, it shows R value less than 0.5, it may be low correlated. Above 0.5 is high correlated. So high correlated values I have to select for my species selection. So I have used for the same. So this may be give a complete feature about. So already I have mentioned about totally 72 features I have in hand. These are the 18 features for all four subbands. So when I use the consistency and correlative measures, so already I mentioned consistency measure is based on the distance, correlative measure based on the correlation coefficient R, and consistency measure find 5 carbons rule I have used, and here it is Pearson's moment I used for the same 0.5. So based on this, both will have, when I mentioned both, these autocorrelation factor in both band 1 and band 2 as met with the criteria above 0.7 and 0.5. For particularly about other subbands and the other things, consistency alone 5, correlation alone 2. So from 72, based on this consistency correlative measure, I have selected only 18 features from the different subbands. I think fourth subband consists of more noise, so the resolution is very less, so no features are selected from there. Similarly, subband 3 also. Subband 3, only 2 features have been selected, but most of the features from 18, it is being selected from band 1 and band 2. Hope you can able to follow me. Any clarification is required? I'm moving fast also some case, right? Because my time allotted is 2 hours. Maybe I want to talk about the 2 methods which I have proposed and used. Is that information is informative or useful to you, or can I move forward? Maybe some input from the participants I required, or from the organizer side also.
Yes, sir, you can move forward.
Okay. Because these are the methods I have developed, so I may be well versed with each and every step. Maybe the participants are the organizers who are available and the students who are available. Maybe need any clarification, particularly maybe at the end of the presentation also, I will ask you the question. Maybe I'll give the clarity. Okay, thank you for the reply. And I can go with the feature selection. I use PCA. PCA is used the covariance matrix development for the selection. And this is the eigenvalue and eigenvectors which are used for the PCA, principal component analysis. Here I kept the eigenvalue above 1 and its eigenvectors are being selected. So based on the Kaiser criterion, okay. So when we keep our value 1 or above 1, maybe it has the high variance. So that is what we have selected, and the output supposed to be original feature matrix with the selected eigenvalues above 1. And based on the PCA, its eigenvalue, eigenvectors, and the from the covariance matrix, out of this 18, I selected 7 features are more prominent towards the more prominent towards the classification. So these 7 features I've taken: autocorrelation, prominence, shared, dissimilarity, entropy, variance, and some variance. The 18 features I have listed here. From this 18, based on the PCA, I come down with the 7 features. These 7 features are basically given to the SVM for the classification. Already I have mentioned both the methods which I would like to explain is a multi-class. So for about this particular explanation, I have 5 classes: stage 1, 2, 3, 4, and normal. Okay, which means negative. So here I have taken 5 classes, so M will be set as 5, 1 to 5. And here I have used the multi-class, so 1 versus rest method is used. So the total images which are considered from LIDC and LCAP databases, these are the databases, publicly available databases for the lung images, lung CT images particularly. So I have created a database, and from there, right, I took 300 images, out of which 70% I have used for training and 30% I have used for the testing. So to 70-30% I have used, and different set also I have tried. If possible, I will present the same. So the steps for the training, I took 210 images for the training with the 7 features and along with the output label. So I know the output label for the training. So it's a supervised classification, supervised learning. So I have used the label. Excuse me. And you used the RBF kernel for the creation of the hyperplane. And these are the tunable parameters which I used. And these parameters are differentiated from the Euclidean distance. And for the classification, initially hyperplane is formed. It is to pose the features in the high dimensional phase. So hyperplane definition or function is being given, expressed here. And with the hyperplane with the RBF kernel, the functions are exhibited this with the parameter called input weight, output class, input vector, and the training instances. M is a training instances, 5 training instances, and B is a bias. K parameters used for the RBF kernel. So as it has the 5 plane, 1 versus rest method which is used. So 5 hyperplanes are there. So for the stage 1 classification, train all the samples with a class 1 label with the +1, because when we have +1, that alone we consider as a class, means stage 1. Otherwise, other labels will be considered as a -1. So we have relay between 2, +1 and -1. The hyperplane is 0, +1 is above the hyperplane, -1 is below the hyperplane. So above the hyperplane, which are considered as stage 1. Below the hyperplane, which are associated with other classes, class 2 means stage 2, 3, 4, and normal, will be considered as a -1. And this method, right, identify the support vectors. And based on the support vector identification, we use the optimal decision boundary for give the value of the same. And based on the optimal hyperplane, we use the proper deduction of the bias and associated weight. So these support vectors is basically used to optimize the hyperplane for the effective computation of the classes, means stages. Okay, for the testing, so far I talk about training. Training is completed with the available 210 images. Testing is happening with the features extracted. Here we will not give the class. The input test image is being given, and the 7 features which are identified based on the RBF kernel which is given, and the class predicted based on the feature high dimensional with a hyperplane is posted, and which are selected as +1 will be considered as the case, consider the particular class. So I may present how I have simulated and bring out the results. Number of images used 300 from LIDC and LCAP databases. So from each database, how many images I took and training testing used. So totally training is used 210 and testing is used 90. So it is splitted here from each database. And the performance measure to prove the method, right, which I used are this: accuracy, sensitivity, specificity, precision, TPR, FPR, and misclassification rates. But effectiveness, I have used computation time as well. So these are the terminologies or the equations which are used for the performance measure: accuracy, sensitivity, specificity, precision. So all it is derived based on these 4 parameters: TP, FN, TN, and FP. TP is actual positive, identifies positive. That's TP. And when you think about FN, actual positive is identified as negative. This is most dangerous. And TN is actual negative and identified as a positive. False positive, actual negative will be identified as a negative. So most of the cases, right, we used to reduce the false positive. That's what we go ahead. And other methods, TPR, FPR, misclassification rate is formulated this with the same parameters: FP, TP, FN, TN. Okay, let me move on for my results section. This is a segmentation results. So this is an input image from the LIDC, and this is the initial contour based on the GSEM method, and the contour is evolved based on the iterative. So here 300 iteration, I took the screenshot and it was like this, and over the 1000 final contour will be evolved this, and based on that the segmented image will be shown. And from the segmented image, the ROA lung region is being selected. This for the LIDC dataset, and the similar thing is for the LCAP dataset. The images are different, and from the pre-processing, I have make it uniform, and I have kept in the database. And maybe I can move on for the multi-resolution thing. DWT is used. This is the band 1, band 2, band 3, and band 4 of LIDC, and this is for LCAP. Okay, next I have used the measures, consistency correlative measures. So these are the discriminative measures which I used here. Discriminative measures, both consistency correlative. These are the features, and the average feature values are determined based on that, right? I have correlated and consistency values. So based on that, the features are selected. These are the 7 prominent features which are selected. Today I have presented over. These are the 7 prominent features which are selected. And which subband is more prominent, that also I evaluated. Maybe subband 1 and subband 2, more features are there. So more prominent features took from the subband 1 and 2. And these are some of the results maybe in my method. I'll quickly run through. So SVM based method, initially it is developed with the ACM, simple active counter method. And when I use this SVM with the new way of segmentation called GSEM, the results were quite improved, and it is authenticated as well. And this for the another values: accuracy, sensitivity, specificity, precision. This TPR, false positive rate, and misclassification rate. And I executed for the computation time as well. So as this method use more prominent, more thing. Okay. So initially, right, the training, it took more time, GSEM method, because we kept as 1000 iteration, but average time also quite high, but accuracy of the prediction is improved. This is one of the area, right, which I have the challenge to reduce. Computation time, quickly we have to take the decision. So computation time is supposed to be less for the decision making. But at the same time, it should not be compromised with the accuracy and prediction. Okay, this is a matrix, the confusion matrix for the deduction. Okay, I'll run through this for my first method. GSM is used for ROI method, DWT multi-resolution, GLCM is used for the feature extraction, and new method, CBH method is used for the feature selection, consistency, correlative, and PCA is used. And based on that, the lung cesium classifier with 5 classifier, 5 with a 5 hyperplane detected. Okay, I completed the first method in the second phase, second module. First module, I have explained about the general theory related with CAD and CDSS and what are the challenges are faced in the CAD method. I have in the second module, I have presented plan to present 2 methods. First method is simply the SVM method, which is used for the thing. There I have initially extracted 72 features from all 4 subbands, and from there I identify some of the features are not very relevant for the decision making. So I infer the feature selection. So that proposed by the evaluated by the method called CBH, consistency based hierarchical method. Consistency measure, correlative measure, and PCA is used. And finally, I took 7 features from there, 7 prominent features I took, and that are used for with the SVM classifier with the 5 hyperplanes. The 5 classes were identified with a suitable method. So, hope the method was understandable. How the decision is being arrived for the application of lung nodal reduction and classification of the stages. Maybe I'll stop here for to check with you any clarification or any doubt. You need any further information related to the method which I have explained. Okay. Hope no further classification, no more clarification is required as of now. Okay, let me go with the second method. Is that quite informative, or somebody can respond? It may be always good. Okay. Thank you. So it's good for the speaker to continue with the same enthusiasm if something useful is there for the participants. Okay.
Yes, sir. It's very informative, sir.
Okay. Thank you. Okay, I'll move on for the second method. Maybe a couple of months and couple of years I spent time for developing all this. I don't know how much really get on with you in the perspective, but if you are not able to understand it in detail, at least you can take it in the conceptual level. So what are the different methods which can be used for the prediction, which can be used for the CAD model? In that concept note, maybe you can take it and maybe you can implement the similar thing on your research or on your platform as well. Okay, so let me move on with the method 2. It is basically, I have changed certain pattern of the method in every level. So since I have developed a new method, GSCM, for the segmentation, and it was prominent and it was quite promising, I use the same here for the segmentation. And the features, I took only 7 features. Maybe I have looked at the accuracy and efficiency and other performance measures. I'm not quite happy with. I have compared with a few methods, but there are some methods are quite ahead of the same. So there I have learned something. It has to be improved the feature set. The different features can be evolved from the ROI. Then it may be useful for the improvement of accuracy. So that is why I have tried here with rotational and scale invariant texture features by using the LBP method, local binary pattern method. And the similar thing, rotational and scale invariant texture features using GLC method also I have evaluated. So the feature set completely I have changed here. And I have selected the shape and statistical. There are 4 types of the features I have selected here. And I checked whether any further improvement in the disease diagnosis or the prediction. Absolutely right. I have used the different classifier, powerful classifier here as a ANFIS classifier. This is a rule-based classifier. Initially, it is if FIS, fuzzy inference. This is adaptive neurofuzzy inference system we have used. So this is the model. This is a model I have used. Pre-processing, GSM method, what I used already for segmentation, the same I took. And LBP features I take. GLCM I took. And apart from that, shape feature and statistical features. There are 4 types of the features I have considered. I extracted from the ROA and I have used the same for the classifications. Okay, let me go ahead with features. Shape features, these are the 7 shape features I have used. Perimeter, area, eccentricity, major axis length, extent, minor axis length, and equivalent diameter. Maybe if I give you the relationship and other things, right, it is quite difficult to explain here within the stipulated time. And the next thing is LBP I have used local binary pattern. So for which 3 by 3 pixel we consider and center pixel value as a threshold. And the neighboring pixel values are changed based on the value of the pixel is 1 if the pixel value greater than the center pixel, otherwise it is 0. So arrange the neighborhood pixels in a clockwise direction and 8-bit binary code which is used to convert to the decimal and replace the center pixel. Here LBP is all about replace the center pixel value and we derive the resultant image with the decimal value. And repeat the process for the entire image. We consider initially for the 3 by 3, but we have to repeat the same process for the entire image or entire ROI of the same. Then scale invariant texture features of the segmented image will be calculated so. And I'll present you what are the features we considered later. And rotation invariant feature here similarly rotation we consider as a 8-bit binary code with a 90-degree 3-bit clockwise we have used, and this result in here also 3 by 3 initially we consider and we do it for the entire image. We do it for the entire image and we calculate the rotation invariant. Here this is scale invariant, this is rotation invariant. Okay. Now I use quite high number of features here as the powerful classifier I used here. So these are the shape features, 7 shape features. I have named give the input to the classifier as A to G. And here these are the rotation features, scale features, statistical features. So rotation and scale features, contrast, correlation, energy, homogeneity I took from both rotation and scale invariant. So each 4, so it is named as H2K and L2O. Statistical features that I have considered here as a mean variance and these things. These also I have named this one. Okay, as of now, you understand that the ANFIS classifier is a combination of these two, ANN and FIS. So ANN is basically a black box approach. We cannot able to understand what is happening inside and how the decision is being taken, how the decision is being made and other things. So the next I went for the fuzzy inference system. We know very well about how the decision is being done. as how the decision is taken, because we only give the rules to take the decision. So here I have used 5-layer pseudotype ANFIS classifier. Okay, now totally with the 4 type of features, I have extracted totally 18 features. So 18, already I explained about, there are some features from statistical, there are some features from shape, there are features from rotational scale in rotational invariant, and there are some features I took from scale invariant. Okay, so totally 18 features I extracted. So this is being implemented here in 3 phases. First phase, I take 3 features in each segment, and the second phase, the 3 outputs of phase 1 in each segment, and the third phase, maybe I'll diagrammatically explain. Phase 3, 1 segment. So here it is so. So totally 18 features, is it? So 6 segments is required. Each segment will have 3 features. So as of now, there are 18. So divided by 3. So there are 6. Okay. Now 2 segments are required. From the 6 segment, each 2 segments are required. From there, so I have I have used a split range function for the effective computation, or otherwise we have to build a more complicated ANFIS network. So when we use the split range, the complex pattern can be reduced as a smaller pattern. Maybe I'll explain through the diagram. So phase 1, 27 into 6, 162 is splitted. Phase 2, it is actually 27 into 2, it is 54. Okay. Phase 3, 3 into 9, it is 1. So totally 225 rules are required. Otherwise, what will happen when we use 3 level? So 18 features, so these many rules. The primary objective of using split range function is this thing. If we haven't used split range function, we are supposed to use 5832 rules. So it is quite complex to understand, derive also. But machine will, when the algorithm will run quite happy, but for the explanation, understanding, this will be good so. By using the split range function, totally 225 features are extracted so. Okay, let me go with the segment 1, phase 1. 3 features A, B, C are taken, and the output will be called as AG1 with the 3 power 3, 27 rules. Similarly, AG2 is calculated and other things. Okay, let me go with this diagram. This being explained for the phase 1. So there are 3 features are taken with the 3 different inference levels, low, medium, and high. And with that, right, there are possibility of 27 combination. This is what I have been mentioned here. With a combination of 3, with the 3 level, we can able to form 27 rules. So these are the rules basically. Functions. Okay. Okay. And let me explain about the first layer. First layer is basically falsification. This layer is a falsification. 1 level is converted into 3 level. The values are falsified based on the range called low, medium, and high. Okay, we have used bell-shaped membership function, and premise parameters are used. These are the premise parameters. Premise parameters are used to define the ranges. And based on that, layer 2 is basically work with the product of inputs from each level. So this is the linguistic labels which are used for Xi, Ya, and Zi. Xi is for A, Ya is for B, and Zi is for C. And layer 3, we actually go with a normalization of the firing strength. So when we do the same, right, this function is being taken, Wi bar. Then the layer 4, we basically use the defalsification. Already we have used the subinotype FIS with a linear membership function, and consequent parameters are represented the same. Okay, let me go with how the rules are framed. The first rule formed for the segment 1 of the phase 1 is given as If A is low and B is low and C is low, then F1 supposed to be P1A plus Q1B plus R1C plus S1. These parameters, P1, Q1, R1, S1 are the consequent parameters. And F1 is a linear membership function, which is actually related with the consequent parameters. Similarly, other rules can be framed such a way. Other rules. This is the first rule. Second rule is low, low, medium. Here it is low, low, high. Can you able to follow me? First rule is low, low, low. Second is low, low, and medium. And A is low, B is low, and C is high. So this is the first set, first phase of the input. So similarly, other rules are framed. Other rules are framed. Totally 27 rules already I have told you. Similarly, rules 6 to 24 are framed. 27 are framed such a way. Now with the aggregate value we'll get. So based on this, for the first phase, first segment, AG1 we will get. Similarly, we will get 6 aggregates. So these 6 aggregates again use as a parameter, use as a feature, and form 2 segments, and we will get the 2 aggregates. From the 2 aggregate, we will form a segment and we will get 1 output. Sorry, 2 outputs, and that will be considered as 1. Hope you can able to follow me. This for the phase 1. This for the phase 1. Defactified output overall is being taken. AG2, aggregate 2 to aggregate 7 are classified are calculated from the 5 different segments of the phase 1. This is the phase 1 output. Similarly, phase 2 and phase 3 will go on. So already I mentioned phase 2, 6 output values of the phase 1 are used and aggregates 7 and 8 are calculated. And from the phase 3, this AG7 and AG2 are used as a features, and AG9 will be calculated with the 9 rules because we have 3 per 2 only. Why it is 3 per 2? Only 2 aggregates and 3 falsified levels in each feature. So stages are classified based on the value of AG9. Maybe I'll present the results over here. So this is a phase we have used for the training. So training, this is a supervised learning. So excuse me. Okay, I'm back to my presentation. Can it visible the presentation? Hope the presentation is visible to all of you. Okay.
Visible, sir.
Yes. Let me continue. So this is a training. Forward pass, we use the initial premise parameters and consequent parameters. These 2 parameters are going to be in a line. So that is called tuning. Okay. Actual output is compared to the target output. So error will be calculated. And this error will be minimized with the help of BP, backpropagation method, through the backward pass. And these values, the consequent parameters are adjusted. Consequent parameters are revised. And this is the updation of the premise parameters. Initially, we assume the initial premise parameters, and based on the error, and it is propagated to the layer 1 with the help of backpropagation, and the premise parameters will be adjusted. That I have mentioned here as a updation. So delta rule for the gradient descent method is used here, and the parameters which are adjusted here based on the premise parameters. This is the initial parameter, and this is the updated parameter ai of n plus 1. Ai of n will be present value, and learning rate also will consider, and t will be the target output, y will be actual output, a is the input source. So similarly, it can be done for the other values like b is 4 to 6 and c is 7 to 9. The output is calculated based on the updated premise parameters and repeat the steps for the number of epochs, bring the error less than 0.01. So learning outcome of training will be this premise parameters and consequent parameters. So consequent parameters are given to the layer 2 for the adjustment of tuning of premise parameters with the help of backpropagation method. Okay, now I can go with the testing. So 18 features which are extracted. Maybe I didn't talk about number of images which are used for training and testing. I'll shortly discuss about. So here I use bell-shaped membership function to think about premise parameter and its linguistic value. So outputs are determined with learned consequent parameters. Stages are classified accordingly. Okay. These are the ranges of values of aggregate 9, or I can say the final output. So the final output value is less than 6, no nodule, 0.6 to 1.5 stage 1, 1.5 to 2.5 to stage 2, 2.5 to 3.5 to stage 3, and greater than 3.5 stage 4 based on the ground truth value of the database. So for the simulation, here also I took 300 images. Used training testing is 70-30. Similar images I used here to check the prominence of the method. The evaluation parameters similar to the previous method: accuracy, sensitivity, specificity, precision, TPR, FPR, misclassification rate. Finally, with the computation time. So these are the results which I'd like to present for the method 2. Rotational and scale invariant features. In the module 2, I explained about two methods which are experimented, which are implemented, how the CAD system is used to come with the decision. One is SVM based classification, another one is ANFIS based classification. Hope you understand about the details. You need any clarification or any doubt or any further understanding is required. Maybe I have move fast while I'm presenting the results and other sections, because when I spend more time, you may not able to conceptually understand about things. Okay, if any clarification required, maybe I'll do that. Then I'll move for my third module. Okay, I think there is no clarification or no discussion further required for the second module. Okay, maybe I immediately move on for the third module. Okay, so with the third module, right, what I'm going to talk about, further avenues for the development of come later. Identify the further avenues for the future use. So for which, right, we have to think about limitations. So when you think about limitations, it is both traditional and conventional method. So it involves high cost for the prediction or for the diagnosis. And we need, maybe I am comparing this conventional method is about clinical trials. Necessity of specialized training for the users or the trained people must be there to take care of the clinical process. And the third one is lack of comprehension regarding real world concepts. So that is one reason this is not well popular. And very importantly, vulnerable to data loss from the digital failures, because the data are saved somewhere and the data is missing. And again, right, we have to go back and collect the samples and we have to evaluate the parameters. So this is one very importantly have to be looked at. And particularly, we have to rely on a single data source, which may be useful for give the solution for the complex situations. So we are actually through the CAD, right? We are deriving to bring this single data source for our systems. Okay, these are some of the limitations. Maybe if anybody is doing your current research or anybody you are planning to do your research in the same domain, maybe you look at these limitations, and any one of the limitations you can take and you can give or propose for a new solution. Maybe it is great to the community, great to the system for the system to be improved. Okay, and in that note, immediately after the traditional and conventional methods, maybe immediate step is about deep learning. So the need for the deep learning as per the innovations or improvement is required. So we need to have some automated task decision, maybe decide the task, split the task into segments, and we can come up with the solution. And the data input is so high. That is also one reason, right, we are moving on the deep learning. So maybe I have used initially 72 features, and that itself, right, it is more irrelevant features, and I use many methods to come down to 7. But deep learning is not so. It is quite easy for use of the same, which are prominent. It will select automatically. What is the main difference between the machine learning and deep learning? Is all about machine learning. We need to extract the features manually or by using some methods. Whereas when you think about deep learning, it will have the feature called automatic feature extraction. So it will select the predefined or its own required features from the input for the decision making. So this is one of the key difference between machine learning and deep learning. So in this note, which I'd like to say, right, deep learning is the driving force behind many modern AI innovations, from the self-driving cars to the advanced medical diagnosis. So we are in the medical diagnosis phase. So in the medical diagnosis phase, the AI, deep learning through AI, right, it is very well used for that matter. Okay. So where to introduce our AI in the deep learning for the CAD. So for the automating tasks, optimizing designs, and creating intelligent workflow for the medical diagnosis, we specifically use deep learning methods on the part of AI. Okay. So what is AI with the deep learning? AI is simply a algorithm, and it is machine learning or deep learning methods to analyze the data and make the predictions, and it gives the suggestions for the improvement and generate the new design to optimize the specific parameters. So, whereas you look at the deep learning, it is a subset of machine learning, but particularly use the processing a large data set. So maybe machine learning in the larger perspective, right, it can use the limited data set, enabling the complex tasks like 3D that I have mentioned, which I have used in the earlier discussion. It is for 2D. Now I'm currently working on with the 3D images for the improvement and prediction. And particularly when we talk about deep learning, the CNN architectures. CNN architectures. So for the CNN architectures, it is image-based diagnosis will be done now, and which are used the convolution layer, pooling layer, fully connected layers for the disease diagnosis like COVID, cancer, and skin disorders. Many more. There's some sample I have given, but many more. The common CNN techniques which are used are GoogleNet, ResNet 50, Inception V4, V3, and all that, right, is well established models. Those who are currently working and going ahead with CNN maybe understand what I'm talking about. And there are some promising models like RNN LSTMs are currently being used to give the effective solution for the disease diagnosis. Recurrent neural networks, RNN, long short-term memory, LSTM, these are the powerful tools particular for the specific applications, and bring out the clinical data, and the comparison the clinical data also is very well possible. So and it is also have the ability to capture temporal dependencies and pattern within the sequence of the varying lengths. So what I'm talking about, patterns within the sequence. So how many different patterns which has in the data set, database. Maybe data, when I talk about database, maybe you can use publicly available database, or you can, for a specific applications like the skin disease diagnosis and so, right, you can develop your own databases. You collect the data from various real-time sources and you can develop so. Okay. Okay, this is the model which is used for the diagnosis. Transformer model, transformer based model. So nowadays, right, it is everywhere, right, we think about multi-model. It's not about binary cases anymore. So multi-model diagnosis, maybe the transformer based. So what is actually the transformer based architecture? Is a it gives the self-attention. It is architecture which gives a self-attention mechanism to integrate and analyze the different patterns. Means type of data like yes, images, text, signals. Only this integration is happen only for the purpose of improvement of the diagnostic accuracy. And we need to look ahead the integration of clinical data with clinical data like genetic, physiological information for the specific prediction with respect to our patients. And now we come up with a specific thing called multitask learning. With the deep learning, now specific advancement is happening in multitask learning for the joint disease prediction. So MTL, it will be generally called as MTL. So MTL is actually multitask learning, which used for the joint disease prediction, which involves a single model or simultaneous prediction models, which can improve the accuracy to identify a pattern or take the decision of so, which can be basically used EHRs, electronic health records, to predict the chronic diseases like diabetics, heart diseases, and strokes. So now, when we think about real time thing, right? A patient associated with multiple disorders or multiple diseases, maybe this tool, the multitask learning tool or approach, which will be very much helpful for them to understand their well-beings, and they can take a proper medication. So with that note, maybe let me wind up my session. Uh, uh, okay, let me summarize what I talked about. So initially, I gave you about the introduction about the CAD, and what is a traditional CAD and conventional CAD, and what is the motivation towards this discussion. And I talked about CDSS and comparison between relation between CAD and CDSS, and the early methods of CAD which are used in radiological pathology and cardiology in different departments, medical departments, and there is a need for integration of system. Maybe in the first module I derived about many theoretical methods what we come across as a CAD, and particularly I talked about in module 2, right? There are two methods which I have worked with, I have developed, and with the results. So SVM with the GSM based lung nodal classification method and ANFIS based lung nodal classification method. And based on that, we try to understand about how this CAD model is used to predict a disease or come with a decision. And the third phase, we talked about limitations of the conventional and traditional methods and need for the further avenues and to develop a new approaches with the deep learning model and deep learning approaches. So these are the things I have talked about. And in the third phase or third module, right, I have given you some enlightening about the further investigation, innovations may require. Still, the researchers or I myself are going ahead with the deep learning with the 3D model, I mean 3D inputs and so. So, if we need to discuss further about those things, maybe it will take further time. Maybe any occasion is there, maybe I'll come up with. So these are my contact details. Maybe those would like to um, get to know some information and some support related to your current project or future perspective. Maybe you please make a note, or you can collect it from the organizers as well. So thank you very much. So thank you once again. Thank you very much for the organizers for giving me this wonderful opportunity, right from the management of Dr. MGR Educational Research Institute and the leadership team of the college and university. And particularly, I thank Dr. K.S. Divya Madam, HOD, and even coordinators Dr. Fariza, Deputy HOD, and Mrs. B.R. Sankari, Assistant Professor, and particularly Ms. Saranya, Assistant Professor, for giving me this wonderful opportunity. Once again, I thank you very much for all of you. If you have any questions or any clarifications required, maybe I'm here for about 10 to 15 minutes. I will answer your questions.
Thank you so much, sir, for the insightful and inspiring session. Your words have truly broadened our perspective, sir. To formally express our gratitude to all who made this event possible, now I call upon Ms. Divya from third year BME, Joint Treasurer of NBC, to deliver the vote of thanks. Over to you, Divya.
Good morning to one and all present here. It gives me a great pleasure to deliver the vote of thanks for today's insightful session of the 5 days virtual faculty development program on recent trends in biomedical engineering, organized in association with the academic staff, college, and Next Gen Biomedical Committee. First and foremost, I extend my heartfelt gratitude to our distinguished speaker, Dr. R. Manika Vasagam, Vice Principal and Head of the Department Information Technology and Artificial Intelligence Data Science, Alpha College of Engineering, Chennai, for taking time out of this busy schedule to grace his session and share his valuable insights with our beloved head of the department. Coordinating. Extend my warm thanks to all participants for your active involvement and enthusiasm throughout this session. Your presence and interaction made this event more meaningful and successful. Once again, I express my heartfelt gratitude to everyone who contributed to making today's session a memorable and enlightening one. Thank you, one and all. Thank you.
Thank you, Divya, for expressing a heartfelt thanks. I would also like to extend our heartfelt thanks to event coordinators Dr. F. Fariza ma'am, Deputy HOD and Professor, and B.R. Shankari ma'am, Assistant Professor, and I would thank our respected Head of the Department, Dr. K.S. Divya ma'am, for her constant encouragement and support. A special thanks to our Honorable President, sir, for this constant guidance and encouragement and support in making this event possible. Have a wonderful day. Feedback link will be posted. After filling the form, you can all leave from the meet.
Fariza ma'am, I'm leaving ma'am. I'm leaving this meeting.
Okay, sir. Thank
Yes,
you, sir.
thank you. Thank you very much.